presence of penicillinase-resistant penicillin. So these drugs are helpful if our patient has already um, taking penicillin, the first generation penicillin, and is not healing, and we will assume that, of course, bacteria, even though they don't have brains, they can be very smart and produce penicillinase um, very fast. And we have, and we the scientists, the medicinal chemists, have able to produce a drug that can combat this penicillinase. So they are called penicillinase resistant penicillins. So we have a very simple example, the cloxacillin, dicloxacillin, and floxacillin. So later on in our individual learning enrichment, I will ask you to differentiate the three. So obviously, the origin of this is the mother oxacillin. Obviously, it has the element oxygen. And then later on, I would ask you how they differentiate from each other. What made the oxacillin became cloxacillin, and later on, we produce dicloxacillin and floxacillin. Was the unique element that made our oxacillin resistant against penicillinase enzyme of our bacteria. And then we have another property by our penicillins. This is called as the extended spectrum penicillins. So extended spectrum, from the narrow spectrum, it will have further activity against gram-negative or other type of bacteria. So one way to extend the spectrum of our penicillin is introduction of an ionized or polar group into the beta position of the side chain benzyl carbon of the penicillin G. And that allows activity against gram-negative bacilli. So what are these ionized or polar group? A specific example is seen with ampicillin and amoxicillin. They have ionized amino group. Okay? So from the very common amoxicillin, if you will be asked, what made amoxicillin very very useful against gram-positive and gram-negative, even in E. coli or in Klebsiella in Haemophilus. Remember the amoxicillin, that stands for amino. Okay? The addition of amino, and amino is an ionized polar group. The same thing with ampicillin. So you have added amino in our structure. Another thing that you can also add is acidic substituent at the benzyl carbon that in the penicillin G that imparts clinical effectiveness against gram-negative bacilli. So the acidic substituent, like our carboxylic acid, it also enhances or extends the spectrum of activity. Okay, so that's the second one. The first one is the polar, the second one is the acidic component. So remember the rules or the principle in organic chemistry that if there's increased polarity of our drugs, of our substances, we can have increased penetration because of our the nature of the cell wall. So it will also allow increase of penetration in the cell envelope of the gram-negative. Okay, so that allows carbonicillin to enter some of the gram-negatives porine channels. So doon sila dumadaan sa porine channels. So this is how a penicillin looks like. Now let's look at the R. So this is the general structure of a penicillin. But what makes it unique, the amoxicillin, ampicillin, carbonicillin, the oxacillin, what makes it unique is their R portion. So the R is the place where we can upgrade. If it is your hero, Okay, this is the part where you can upgrade to make it better, to make it unique, to make it not a generic one. So for penicillin here, we will dissect it. So let's start with the unique beta-lactam ring, this one. So this is untouched. This should not be altered to maintain antibacterial property. And then we have here the thionamycin compound, but the sulfur atom can be omitted. So some penicillins later do not carry sulfur. And then, as you can remember kanina, acidic substituents will enhance our spectrum of activity. So this one, our carboxylic acid here, this one helps the extension of the spectrum of activity. And then we'll move forward here with the N here. It is a polar ionizable group that also allows extension of spectrum of activity. And then this one here, okay, this is constant to all penicillins also. This is helpful for our penetration. Double bonds, they are non-polar, so that will equalize our polar structures here. So what we have to equalize, or we have to at least make it to the point na pantay si polar and si non-polar, because if it's too polar, it will readily excrete our body. Okay? If it's too non-polar, it cannot pass through other compartments, or it will be too lipid soluble. Too lipid soluble drugs tendency to have very fast action. So we really have to make it balance. So our acidic compounds, our polar compounds are being balanced by our double bonds, which are non-polars or lipid loving. And then we have the R group. So this R group is the part again where we will upgrade. So if the R group is bulky, when you say bulky, it has conjugated rings, it has double bonds, it's a long chain ring, it will be favorable for the drug against beta-lactamase enzyme. It will make your drug beta-lactamase resistant. So it will not be inactivated by the beta-lactamase enzyme. Okay? Now, if our drug here, the R, will be substituted by an electron withdrawing group, like your amines and your oxygen, it will allow acid resistance. So acid resistance allow oral administration. It won't be deactivated by our gastric juices. Okay? So it favors oral preparation or oral administration. Kung absent siya dyan, yung presence of electron withdrawing group, that's the time na we will give it via IV. Okay? Now, if our R here will have also a polar group, as mentioned a while ago, and an acidic group, it will make our penicillin broad spectrum. Okay, so that is the general structure of our penicillin. So moving forward, this one, the one in circle is the R group. So that is a very broad, bulky structure. So this structure contains a bulky one and an amine. So if we will go back to our discussion here, a bulky group allows beta-lactamase resistance, and presence of amine allows oral administration. So if you can see this one, looking at it, just by looking at it, if I will ask you at this point, what kind of drug is this structure, you will try to look at this ring. Then you can answer, it's a penicillin or it's a beta-lactam drug. What kind of beta-lactam drug? So this one here, though it does not look like a house in the structure, but natabingi siya, comparing to the structure that you can recall with cephalosporin, which is a piatos, carbapinem, which is a pentagon, and then without the S, and then the monobactam. So obviously this one is penicillin. So penicillin is the answer. Now, if you will be asked if this drug can withstand penicillinase such as beta-lactamase and acylases, then you will look for the R part. This one is the R part. If it's carrying a bulky structure, yes, it has ability to withstand penicillinases. Can you give this via oral administration? So you will look for presence of amine and presence of acidic compounds. Then if yes, there is, you can give it via oral administration. Okay, so I hope that helps us later on in facing our dilemma with the structure-activity relationship in relation to our mechanism of action. Another example is this one. So it's just almost the same, but it's not the amine right now, but it's the acidic compound, our carboxylate. So these are examples of our penicillins, and they have the unique R group here. So for penicillin G, this is the unique R group. Penicillin G and penicillin V almost have the same R group, but of course, we need to add polar groups to make our drug available orally. So that's addition of our oxygen here. That is an ionizable polar group. And then we have methicillin, naphthalene. These are penicillinase-resistant penicillins, di ba? Methicillin, naphthalene, oxacillin. And as I have mentioned a while ago, in order to become penicillinase resistant, you need to have a bulky structure. So this is how a bulky structure looks like. This is for methicillin, naphthalene, oxacillin. So that's the structure of oxacillin. Dicloxacillin, this one, and ampicillin.